Mediterranean coasts have experienced centuries of continuous progradation, largely due to strong soil erosion on the inland as a result of deforestation with brief phases of retreat, when demographic collapse led to the regrowth of the Maquis shrubland, just like in Italy after the fall of the Roman Empire, or with the spread of the plague in the 14th century. The earliest known network for monitoring coastal evolution consisted of 3 milestones placed by the Lorraine family north of the mouth of the Arno River in 1828, on which the distance to the sea was receding rapidly was engraved, requiring the construction of new coastal towers. Today, the concern is the opposite phenomenon, with erosion affecting most Mediterranean beaches. Although erosion is part of the natural processes that continuously reshape the Earth's surface, the causes of its recent and rapid spread are to be found in human activities, such as the abandonment of agriculture, the construction of dams and weirs along river courses, the extraction of aggregates from their beds, and land reclamation. Sediments flowing along the coast are not free to move due to artificial obstacles such as ports, jetties, and shore protection structures. The effect of these actions is not always calculable with accuracy and may manifest itself over different timescales. This is why it is necessary to keep the coast under observation in order to quantify the changes and to predict future developments. In addition to a medium-frequency monitoring for all coasts, a more frequent control must proceed, as well as accompany and follow the construction of works which may affect the natural evolution of the beaches. In this case, the sector to be monitored must correspond to the physiographic unit, that is, the stretch of coastline delimited by promontories or structures that reach the sea beyond the depth at which the sediments move due to wave motion. For minor interventions, smaller but morphologically homogeneous sectors can be considered. An in-depth knowledge of the current processes, their past and future scenarios, can lead coastal zone management towards defense, adaptation, or strategic retreat. When defense works are built, they reduce the resilience of the coast and require periodic maintenance and changes to fit with future conditions. Adaptation, instead, entails modifying the anthropogenic structures on the coast in order to guarantee their functionality also in future scenarios. Retreat is considered the most sustainable strategy in environmental and economic terms if the time horizon of coastal planning and management is extended, as it should be, to include future generations. In this case, the analysis of past processes and the monitoring of present ones will provide data for the models that will have to predict, at different levels of certainty, the position that the shoreline will reach in the reference time. Obviously, sea level rise will play an important role in this prediction. Up till now, it has been a secondary cause of coastal erosion, but in future scenarios, it will be a dominant factor. Land management always required the informed participation of citizens. But in this case, this need is even greater, since the choices made will have a considerable impact on the population and will also have an irreversible effect on future generations. This is why data on the evolution of the coastline, causes of its erosion, and the scenarios that the models will produce for the coming decades must be disseminated as widely as possible to a population that not only must be informed, but also familiar with its strategy. The reconstruction of what happened in the past, the analysis of current trends, and the prediction of future scenarios must be based on suitable data for the description of the various processes in the spatial and temporal resolution, which is specific to each situation. The historical evolution of coasts can rely on ancient cartography, but what needs to be taken into account is the context in which each document was produced, as well as its purpose. Pre-geodetic cartography can provide indications on the general shape of the coastline and on the presence or absence of certain elements, but any numerical analysis clashes with the poor accuracy of cartographic methods of the time, except in the presence of major morphological variations. The reprinting of maps at a later date poses the problem of attributing the correct date. Although cartographers rarely focused their attention on the position of the shoreline, which has always been considered extremely variable, geodetic cartography is able to provide much more accurate information. The major temporal separation between the various documents ultimately leads to a simplification of the way in which coasts have evolved, giving us a picture in which the transformations are necessarily considered linear. The documents produced using air surveys do not always take into account the displacements of the apparent shoreline caused by the astronomical tide and the barometric tide, displacements which in shorelines made up of fine sand, and therefore with a low slope, can lead to greater errors than the actual value of the phenomenon to be evaluated. The various references which are visible on the beach and which can be used as position markers of the shoreline, for example the wet beach limit, debris line, midpoint on the foreshore, are all affected by the conditions prior to or during the air survey. Only the isoipse, or zero isobath, is a topographic feature, whose position can be compared over time. Sometimes it may be surfaced and sometimes submerged, but the presence of water is not considered in the survey. One element to be taken into account when interpreting monitoring data is the inherent variability of the shoreline. Short-term changes, days, weeks and months, are often greater than the longer-term rates of movement, that is, the evolutionary trends. The health of a coastline is not only given by the position of the shoreline. A stronger indicator is its sedimentary balance, that is, the variation in volume of the whole beach, both the emerged and the submerged parts. The former extends from the foot of the dune or artificial structures to the shoreline, while the latter reaches the depth of closure, that is, the depth beyond which the morphological variations highlighted by the bathymetric surveys and induced by wave motion are not relevant. Regardless of the instrumentation used on the emerged beach, the accuracy of the current surveys is greater than the size of the microforms present on the beach, such as ripple marks, and the estimation of the volumetric variation of this part of the beach is very accurate. Bathymetric surveys, on the other hand, are accurate within a few centimeters, and in the comparison one cannot avoid over or underestimating a change in elevation of 5 to 10 centimeters. If one considers the extension of the submerged beach, which, depending on the slope of the profile and the depth of closure, can reach up to 1 kilometer, one can understand that the error in the estimate of the sedimentary budget can be significant. While a survey with a higher density of points is preferable on both the emerged and the submerged sectors of the beach, high-density surveys, for example with laser scannel on land and multi-beam in the sea, are not always favored by the cost-benefit analysis. With uniform morphologies, that is, in the absence of macrocusps and non-linear bars, and obviously without rocky outcrops, the survey on close profiles can reproduce the shape of the beach in a way that is compatible with the one generated by a high-density survey. In any case, the monitoring protocol for this aspect has to be functional to the specific question it has to answer. The accuracy of the data, as well as their spatial and temporal frequency, must be defined case by case if the best cost-benefit ratio is to be achieved. It goes without saying that this does not apply to continuous monitoring at a regional scale, which has to produce comparable results between the different sectors of the coastline. An important part of coastal monitoring is the study of sediment texture evolution, especially if it is aimed at assessing the impact of sea structures on the effectiveness of artificial beach nourishments. This too needs to cover both the emerged and submerged beach, and be based on a number of sampling points that take into account that beach sediments also have horizontal and transverse variability, and that coastal structures can influence erosion, transport, and deposition processes, so that their impact can also be assessed on the basis of sedimentological data. In the case of artificial beach nourishments, whether they occur with materials coming from the sea or from the land, which rarely replicate the grain size distribution of the native sediments, the collected data must be able to show how the new materials evolve over time. Also, to provide useful information for the definition of the characteristics of the sediments, which can then be used in future beach replenishments. The processing and representation of data is a fundamental monitoring step, and these activities must be set up at the same time as all other operations, even those that precede them. The way in which a certain set of data has been acquired determines the subsequent possibilities for its processing and representation. The comparison of data collected in a random way, or in any case not specifically designed to provide the required answers, is unlikely to provide the information that the designer or planner needs. As far as the analysis of the shoreline evolution is concerned, the comparison carried out along transects provides an approximate evaluation of the surface variations of the emerged beach, in particular when it does not have a regular pattern. On the contrary, the calculation of the areal variation on each suitably defined stretch of coast gives a real measure which also takes into account the discontinuities produced by the defence works and the cusps migrating along the shore. In defining the sectors, compromise must be found between the uniformity of their length and the need to close them in correspondence with particular morphological elements, be it anthropic or natural, for example, mouths, headlands, ports, coastal defences, etc. The classic representation is made up of histograms, showing for each sector the average displacement or rate of displacement of the shoreline. When comparing histograms representing different periods, it is essential to keep the vertical scale constant and not rely solely on programs which automatically use the extremes of values to set the scale. A synthesis of the information on a long coastal stretch can be made with a pie chart, where the class size has to be carefully defined. Positive or negative variations of the same order of magnitude in the accuracy of the surveys can be placed in a single class called modest variations, possibly separating the positive from the negative ones, while with the range in which the displacements are greater, a scale with intervals of increasing amplitude can be adopted. This avoids that a few sectors with very strong variations force a representation that masks the differences in behavior among the other sectors. The reading of the orthogonal profile of the beach in its emerged and submerged parts and of its variations provides useful information on its morphodynamic state, on the impact of the works, and on the stability of artificial nourishments. Since the slopes are modest, except for a few sections of the profile, such as the dune and the foreshore, the scale of representation must be altered, producing a certain vertical exaggeration. If the scale ratio between height and length is high, for example 1 to 2, it will be very difficult to perceive the presence of certain morphologies, such as the crests of the berm, the step, and the bars. If on the contrary it is too low, for example 1 to 10, these shapes will be very evident, but the perception we will have of the profile will be distorted and far from reality. In the representation of the data, errors or inaccuracies in the survey may emerge, which sometimes produce a very evident pattern. A classic case is the temporal decoupling of position acquisition and depth measurement. The delay of one in relation to the other creates a ripple in the isobaths caused by the dragging of elevations towards the shore or out to sea. When comparing bathymetric profiles or bathymetric charts produced by surveys carried out at a later stage, it must be remembered how much the low accuracy of the data in the submerged part affects them. Variations within the limits of accuracy should be regarded as uncertain, and the scale of vertical variations be set accordingly. Rather than volumetric variations, which, if they remain within a certain accuracy range, can lead to erroneous assessments, it is changes in shape that are most significant, such as grooves along reefs, pits at the head of groins, or displacement of bars. When it comes to comparisons between closely spaced surveys, it is sometimes more appropriate to limit the analysis of the sediment balance to the emerged beach and a narrower band than the submerged one, to avoid errors over the wider area being too large. It is evident that the weather conditions occurring during the considered time period should be taken into account whenever possible when analyzing the data. This is not easy for data collected in the past, but monitoring occurring at present, in particular when it comes to assessing the effectiveness and the impact of maritime works or the stability of artificial beach replenishments, cannot disregard the acquisition of wave data. The same must be said for the maritime works and for all that which influences the sedimentary budget of each physiographic unit. And the data acquired must also be read in the light of the age and typology of the various interventions, as well as any structural modifications made over time. In view of the fact that the choices that will have to be made on the basis of the monitoring results will involve all the stakeholders on the integrated management of the coastal strip, they will have to be easily accessible and comprehensible. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . The identification of the causes of erosion, the quantification and localization of erosion processes, and the analysis of their evolution over time are some of the purposes of morphological monitoring. On a national scale, if data are collected and processed in a homogeneous way, they will make it possible to assess the intensity of the process and to define the resources needed for the overall management of the phenomenon. The conformity of data and their elaborations will also allow the prioritization of interventions and the value of resources to be allocated to different parts of the territory. As far as coastal defense projects are concerned, the data produced by monitoring will allow not only the assessment of their effectiveness and impacts, but also the setting up of interventions for the mitigation of negative effects, and those possibly necessary for the optimization of structures. In the case of artificial nourishments, it will be possible to plan interventions for the reconstruction of the volume and the possible modification of the texture parameters of the sediments to be used. Interventions do not necessarily mean structural ones, since the regulatory ones are just as important for a sustainable management of the coastline, perhaps even more. Data produced by the monitoring will allow the development of suitable models for the creation of future scenarios, with variable time horizons and according to the various levels of uncertainty in the quantification of the various forcing factors. Depending on the different morphological, ecological, economic and social characteristics of the various coastline stretches, management strategies will have to be defined on which individual intervention projects can be planned at a later stage. To date, defense is the strategy adopted in almost all parts of the world, building hard structures that prevent the shoreline from receding, reducing the energy of incoming waves, or capturing sediment in transit. This leads to the expansion of erosion to the downdrift stretches, as well as the morphological and sedimentological transformation of the coastline. The resilience of the coastline is significantly compromised, and the system is no longer able to adapt to any increase in the intensity of the forcing waves, wave energy, sea level, frequency of extreme events. The environmental and economic value of the defended coastal stretch decreases as the structures become more imposing, and it may happen that the defense costs more than the value it ends up protecting. Moreover, as erosion processes become more and more frequent, future generations will be forced to bear progressively heavier burdens. Any subsequent change in strategy would result in a waste of previously deployed resources. Adaptation consists in modifying structures, buildings, communication routes, harbors, etc., in such a way as to guarantee their functionality, even in the considered environmental scenario, without setting them back. Artificial nourishments, since they modify the sedimentary budget of the beach without foreseeing its retreat, can in fact be considered as part of this strategy. Strategic retreat is considered the most sustainable strategy in a coastal zone management with a wide time horizon. This stems from a scientifically based definition of future scenarios, albeit with the limits of certainty of the quantification of the forcing factors at play. By extrapolating the position of the shoreline as a function of current trends, including predicted sea levels, and simulating a series of consecutive high-energy storms, one can predict where the shoreline will be in the reference year, for example 2100. This, in turn, defines the setback line, beyond which no stable structures may be built, and in the event of damage to existing structures, they may not be rebuilt except behind this limit. In addition, the relocation of structures before their collapse should be encouraged, both by economic and regulatory means. The strip of land affected by these actions should not be considered as abandoned, but will require as much or perhaps more attention than the defended sections. The public investment will also have a direct impact, since the setback area acquired for common use and equipped with removable structures will have a high recreational and social function. It is clear that this strategy requires a strong knowledge, sharing and full participation of all stakeholders to achieve the goal. A fourth strategy is to address the causes of erosion. In many cases, monitoring allows the identification and quantification of the causes of erosion and provides planners with the necessary knowledge to take action and assess the long-term cost-benefit ratio. Once the sedimentary deficit of a physiographic unit has been defined, it will be possible to evaluate if some interventions on the catchment area will be sufficient to increase the river's sediment supply, allowing the development of landslides, reduction of weirs, elimination or emptying of buried reservoirs. And in any case, it will be possible to evaluate the hypothesis of realizing a sediment bypass. On the coastline, monitoring will have made it possible to quantify the volumes that are blocked by projecting structures not intended for coastal defense, such as ports and jetties at river mouths. In these cases, a continuous or periodic bypass of sediments can be envisaged, not forgetting that the borrow area will also have to be monitored to assess its effects and leave sufficient volume to contain extreme storms. At the level of coastal planning, monitoring and forecasting models of future scenarios will form the basis not only for defining the setback zones, but also for the type of settlements and structures to be built in apparently stable areas, and in those undergoing progradation for processes that past history and forecasting modules could make us recognize as ephemeral. Monitoring, which at first glance may appear to be just a trivial measurement exercise, turns out to be a tool for knowing to govern, which is the basis of political action.